This is VO1 RFX, and let's take a look at what's on the bench today. So today we have a home-built RF dummy load, which I put together about 2 or 3 years ago, and I've recently modified it to have a sample out jack. This dummy load is rated for 100 watts, at least momentarily, with an SWR of 1.5 to 1 or better from 0.4 megahertz to 50 megahertz and 144 to 148 megahertz. The particular RF power resistor that's used in here, which is a single 50 ohm 100 watt resistor, is a bit unusual in its RF performance in that it is capable of providing a good match in the HF spectrum and then fails to do so quite spectacularly above HF, and then comes right back into a good 1.5 to 1 or better match in the broadcast FM and then 2 meter band. So, quite conveniently, it decided to kind of get its act together just in time for the 2 meter band. There's three main things I'd like to go over today with this unit. The first is the construction and the design. The second is the schematic of the RF sample output that I've added, which is very straightforward. And the third is a brief demonstration of how this unit works when it is connected with a radio and an oscilloscope. First, taking a look at the design and construction of the unit, it's probably fairly obvious that this dummy load is built into an old small paint can. It's filled with mineral oil on the inside, and for the lid, we have two holes that we've drilled, put through on the drill press with a step-up drill bit to accommodate our two BNC jacks. Of course, this was originally conceived as just a dummy load, so there was no thought for an extra jack in terms of hole placement or spacing. However, that decision was made for us very easily because of this very large aluminum heat sink, which was came out of an old Bose speaker, I think, that had the misfortune of being broken while simultaneously coming across my bench. And it's JB welded to the bottom third of the paint can lid, which makes the only appropriate place for another jack to go being in the top third. The only things left to mention in terms of construction are that both BNC jacks are sealed using silicone sealant around the perimeter on both the front and back face of the paint can. So this is with the intention of preventing a spill if the dummy load should be knocked over by accident. The rim around the paint can, of course, would protect the contents from spilling out had we not drilled two very large holes in here. And the last note that I will cover on construction is that, of course, we have all point-to-point wiring here. And the situation here looks much more um, complicated than it is. We have a large network of resistors here, and that's simply because I did not have the correct resistor on hand. I needed something with, I believe it was 4 watts of power rating or wattage, however you'd like to say it. And I did not have anything nearly in that range for the value that was required, which was 10 kilo ohms. So I simply used 16 quarter watt 10K resistors, and they are chained together. So four are put together in series, and then four of those four in series are put together into parallel. And then we end up with a 10 kilo ohm resistor, logically a 110 kilo ohm resistor with a much higher power dissipation rating. Similarly, for this sampler, 50 ohm sampler resistor that we'll talk about in the schematic later, these are three 150 ohm resistors that are also quarter watt. And it is all point-to-point wiring. It does look a little bit, I don't quite think there's a word for how it looks. I mean, these resistors here. Obviously, this is a little bit difficult to put together. The lead length is quite short, and that's deliberate, as not to cause any RF demons to haunt this device. And these resistors are essentially in place using a combination of mutual admiration and a sense of learned helplessness. But the solder joints are clean and shiny, so that's good, and it works. The fact that it works is, probably the most important thing. And lastly, we've used enamel magnet wire here. Just on the off chance, I had a bit of a sneaking suspicion that maybe if I used regular hookup wire with PVC or silicone insulation, that maybe being submerged in mineral oil constantly could possibly cause the insulation to get a bit funny and maybe loosen or something like that. It's a long shot hunch, but I had the enamel magnet wire anyway, so I figured why not use it. And that's functionally it as far as construction goes. The heatsink is JB welded here to the paint can lid, and the power resistor is bolted into this heatsink with some holes that I drilled on the drill press so that it's held in place. And then the paint can lid simply just goes onto the paint can, and this is acting as just one very large heat dissipating device and is actually completely optional, um, provided you are staying within a certain power range and not keying up for extended periods of time. You can just use the device like this. But of course, that's not very convenient, nor is it very pretty. So we can hide all of the kind of ugliness that we've created here by simply dunking it into our paint can. Next, let's take a look at the schematic. So the first section that we have here is our dummy load. And in the case of this design by Kilo Papa 4 Mike Delta, they've chosen two 100 ohm resistors in parallel that are 5 watts each, which provide the 10 watts in their 10-watt dummy load. It's worth noting that when I converted my unit from being a dummy load to being a dummy load with the RF sample jack, I essentially ended up building this. So you could say that I started with this part of the schematic, just a dummy load, and I ended up with this. Now, the difference between what I built and what's depicted here is in the sampler network here. And it's as superficial as change in component values. So they have four 620 ohm resistors. So they've got 2,480 ohms here. It's difficult to write at this angle. 2,480 ohms there. Whereas in mine, it's 10K. 10 kilo ohms. That pen is really getting away from me. It's not easy to write at a right angle. And then we have the sample terminator here. So this, again, is identical to what I have. It's just superficial in that they chose two 100 ohm resistors. I chose three 150 ohm resistors. The point is that this is supposed to be 50 ohms. And so is this, of course, as that's the dummy load. So that's really all there is to it. As far as how the circuit actually works on a deeper level and how the attenuation works and all that sort of stuff, I would refer you to someone who is not me. I'm not an electrical engineer. I'd be doing you a disservice to give a lecture on circuit theory or anything like that. But you can look up this design here. It's Kilo Papa 4 Mike Delta designed it, and it's if you just Google 40 dB attenuator 10-watt dummy load, you'll find it on the internet. And that's essentially all there is to the circuit. It's really quite simple. Okay, so let's conclude with a demonstration of how we would use the sample out jack from our dummy load in a bench testing or repair scenario, because functionally this is a piece of test equipment, albeit not a anything professional grade, but it's certainly better than nothing because it allows us to see the output of a radio and its waveform on a scope, which is quite handy. So directly below the camera's view here, I have a Midland 13866 CB radio from the mid-1970s, which is in a bit of disrepair. It has a few issues with it. And one of those issues is actually both the reason we're going to use this radio for this demonstration, and it's also actually going to help us demonstrate how this works. And you'll see what I mean shortly. So let's power on our radio. We're running this off our bench power supply, and we've got it voltage and current limited while we're working on it here. So when we key up the radio, and goes without saying that we have the RF output jack of the CB radio going into the input on the dummy load, and then we have our sample output jack connected to our oscilloscope, and we're using the 1 meg ohm setting on the oscilloscope. And when we key up the transmitter, we see that we have a sine wave, just a pure sine wave, not a modulated sine wave, just an RF carrier. So that's quite interesting because that happens to be one of the things that's wrong with this radio, is that it's not modulating. I think the issue is most likely in the microphone. It is held together with hopes and prayers, and if we can get it on camera here, it's of course disassembled, but it's quite a piece of modern art. This microphone is. So next up, we'll be taking out the signal generator to essentially replace the microphone, if we can do so. Although the switching mechanism in the microphone is actually integral to the circuit of this CB radio, and turns out this radio does not work when the mic isn't plugged in. Ask me how I figured that one out. But let's go back to the scope here and key up again. So we see our carrier wave, and we are at 200 millivolts peak to peak. And it even picks up an estimate of frequency at 27.0551 megahertz. And I can't read the dial because it's upside down and a little lopsided. It's not quite on track. But in any case, 200 millivolts peak to peak, that's a pretty interesting piece of information for us because if we work backwards from that, knowing this is a 4-watt radio, then we can essentially figure out how many volts we would see going into our scope if we put a 100-watt rig in here, or a 200-watt rig, or what have you. And so we can get an idea of what kind of voltages the scope is going to be seeing, and by extension, what kind of radios we should not use with this sample out jack. In other words, what kind of attenuation values are appropriate and which ones aren't. But if you head to an online calculator and work out how many volts is coming out of this radio, and you'd be able to quickly see the amount of attenuation that's being performed. I'm probably going to put it on screen somewhere right here, maybe. Actually, to be completely honest with you, I'm going to put the text wherever it's most convenient, not going to put it on my hand. But based on whatever value is on screen that you are seeing now, that's telling us how much attenuation that we're actually having, or how much attenuation we are, how much we're attenuating the signal by is what I should say, which is very useful to know, because the main goal is to not blow up the oscilloscope, right? And especially when you're fixing radios and that sort of thing, the best way to fix something is by not breaking it in the first place. And I don't know how to fix oscilloscopes, so my plan is to not break the one I have. Hopefully you found this video useful or entertaining, or ideally both. This is VO1 RFX, and this is what is on my bench today. Thanks very much for watching.